Use part 1 of the fundamental theorem of calculus to find a derivative of the given integral from minus 4 to x square root of t cubed plus 64 dt. Well, I will first surprise you with the answer. The answer will be the function inside of this integral, but the variable t disappears and will be substituted with the variable indicated here, because now we're differentiating with respect to that variable. So it becomes x instead of t, x cubed plus 64, and that is the final answer. Well, I will explain it a little bit in more details so you also don't assume that it's always the case. Fundamental theorem of calculus basically says if you have an integral from a to x, f of x dx, and now I will make a very important point that there's another variable involved. In this case it's t, but it can be s or whatever. And you remember this variable called a dummy variable. Basically, it's not important which one it is, it's just a variable of integration. But then we're differentiating all of this with respect to variable x, like so. And that's where we claim, basically what the theorem says, that the answer will be that function, but of the variable x. This is how it sounds more professionally. Fundamental theorem of calculus, part 1, says if f is continuous function on the closed interval from a to b, and it is, at minus 4, the square root becomes square root of 0, and then after this it's continuous, then the new function that is basically a cumulative function from a to x, f of s ds, is also continuous on AB and differentiable. Moreover, if I differentiate it, it gives me the function inside of the integral, but over variable x. I wanted to show you graphically. I think many of us are visual learners, so that might help. When I'm asked to find the integral from a to b, the square root of t cubed plus 64 dt, I kind of remember that it means I plot a graph of t cubed plus 64. So this is t, this is y. Here's the graph in front of you, and then I'm asked to find the area from a to b. In our case, it's from minus 4, so it's over here, and to whatever b that is random. So here is the area. Tuk, tuk, tuk. Here you go. The thing is, b was not fixed, right? They gave us x. That means the upper limit of integration is changing. That's why it's called x, right? So it goes to the left or to the right, can be bigger, can be smaller. If b becomes bigger, then there are more to accumulate. If b becomes smaller, then the area shrinks. And that's kind of how I understand what a cumulative area is. That's what integral gives me from minus 4 to x. Now, when I differentiate that integral with respect to x, I'm asking a question. How fast does this area accumulate? Well, it accumulates as fast as the shape of the graph. So it accumulates fast at the beginning, accumulation slows down, then it accumulates super fast over here, so it depends on the curve. That's why it makes sense that the answer gives me exactly the function we see inside of the integral. How fast? Here it is. This is the phrase. How fast does the area accumulates, increases or decreases, right? This fast, the shape of the curve fast. It will be a little bit more complicated if you will see not x, but say x cubed or any other function of x, and that will be in our other examples in this chapter.